Thank you. Thank you. Thank you very much. I'm Philip Emeagwali. My scientific story is more fragmented than the story of the theoretical physicist Albert Einstein. It was the story of my journey from the frontier of extreme-scale computational physics. That journey to discover how to solve the toughest problems in mathematical physics was interrupted during the last 30 months of the 1960s. That journey was interrupted when I fled from my all-boys Catholic boarding school named St. George's Grammar School, Obinomba, Nigeria. I fled from St. George's Grammar School in late April 1967, and I fled because the Nigerian Civil War was in the air. I fled to become a 12-year-old refugee in the breakaway and short-lived nation of Biafra. 2 months after I fled from Obinomba, Nigeria, to Abo, Nigeria, to Onitsha, Biafra, and on the 6th of July of 1967, that Nigeria-Biafra War began. On the 4th of October of 1967, my ancestral hometown of Onitsha, Biafra, was heavily bombarded for 24 hours and bombarded from Asaba, Nigeria, and bombarded from across the River Niger. The following day, that artillery bombardment of Onitsha, Biafra by the Nigerian army was followed by the invasion of my hometown. That night, Onitsha was invaded by a 10-boat armada that carried 5,000 Nigerian soldiers. Those Nigerian soldiers were led by Moitola Mohammed, who would later become the president of Nigeria. 1 in 15 Biafrans died when that Nigerian Civil War ended. That Nigerian Civil War was a nightmare and a bloodbath. The Nigerian Civil War ended after 30 months of non-stop fighting, and on January 15, 1970, 1 million soldiers died at the war front of the Nigerian Civil War, and about 500,000 women and children died in Biafran refugee camps. I survived 2 years in Biafran refugee camps and survived 6 months of bloodbath near the Oguta war front. I survived a war that was described as Africa's bloodiest war. Biafra was located in the southeastern region of Nigeria, West Africa. My family of 7 children lived in 6 refugee camps within Biafra. For 2 years and 3 months, onward of April 1967, my family lived in refugee camps in the Biafran cities of Onitsha, Ogidi, Oba, Oka, Oketiti, and Ndone. Russian Ilyushin bombers and MiG fighters were bombing and strafing our neighborhoods of around 14 Mba Road, Onitsha, Biafra. On my 14th birthday of August 23, 1968, my postal address was Chukura Philip Emeagwali, St. Joseph's Refugee Camp, Oketiti, Biafra, West Africa. On the cover of the Time magazine that was dated August 23, 1968, is an artist's portrait of Colonel Ojukwu, the leader of Biafra. The cover story of that issue of Time magazine was titled Biafra's Agony. For us, the agony was real. Half of the refugees at our St. Joseph's refugee camp, OKTT, Biafra, were living skeletons. My father, Nnameka James Emeagwali, was the live-in refugee camp nurse at St. Joseph's refugee camp. In August 1968, my father told me that half of the children in our refugee camp, including my 2-year-old brother, Peter, had kwashiorkor, a rare malnutrition disease caused by lack of protein. At St. Joseph's refugee camp of OKTT, Biafra, children and grandparents that did not survive kwashiorkor were buried without funerals and buried at our backyard. In Biafra, meat, pepper, and even salt were almost as scarce as gold. 3 charity organizations, the Red Cross, the Roman Catholic Relief Organization named Caritas, and the World Council of Churches, provided to our refugee camp corn meal, Norwegian dried stockfish named oporoko, and powdered milk. The relief foods were secretly flown into Uli airstrip of Biafra. That 27-month refugee experience was the reason the United Nations has the portrait of Philip Emeagwali along with the portraits of the likes of Albert Einstein in its gallery of refugees who made a difference. In July 1969, and at the banks of the River Niger at Ndone, Biafra, I was conscripted at gunpoint and conscripted as a 14-year-old soldier into a war that was on par with the American Civil War or the Spanish Civil War. Without any formal training as a soldier, I was marched at gunpoint to the Biafran side of the Oguta war front. At Oguta war front, Biafran soldiers were living on less than 1 cigarette-sized cup of gari a day. Gari is pulverized fried cassava root. Biafran soldiers added palm kernel nuts and water from the Oguta lake to their gari. When I arrived at Oguta war front, some Biafran soldiers had gone for days without food and they were threatening to leave their holes. After 48 hours without food, I became woozy with hunger. Because there was nothing to eat at Oguta war front, I was immediately reassigned to the officers' mess or kitchen of the Biafran army at Ndone. 2 months before my arrival at the Oguta war front, Biafra, and in May 1969, Murtala Mohammed, who would later become the president of Nigeria, and Mohammed Shua were given command of the Nigerian army at Oguta war front. In late May 1969, and 2 months before I arrived at Oguta war front, Mohammed Shua had defeated the Biafran army and captured downtown Oguta. A few weeks later, downtown Oguta was recaptured by the Biafran army, but recaptured after a loss of 500 soldiers. I was conscripted into the army and conscripted at the market at Ndone, Biafra. I was conscripted to replace one of the 500 Biafran soldiers that died in the battle to recapture downtown Oguta, Biafra. The Battle of Oguta War Front was personally commanded by Odumegwu Ojukwu, the leader of Biafran nation. When I arrived at Oguta War Front, Joseph Hannibal Achuze, nicknamed Air Raid, was commanding the Biafran soldiers. I learned that Olusegun Obasanjo, who would later become the three-time president of Nigeria, was commanding the opposing Nigerian army at the Oguta War Front. Olusegun Obasanjo arrived in Oguta War Front in July 1969 and arrived at the same time that I arrived in Oguta War Front. In July 1969, I arrived at Oguta War Front and arrived as an untrained soldier and arrived at about the time Colonel Olusegun Obasanjo arrived with 10,000 trained soldiers. Those Nigerian soldiers killed or wounded 2,200 Igbo civilians. In July 1969, Biafran soldiers were trained at the war front. Biafran soldiers were only trained to aim and shoot to kill. 3 months after I arrived at Oguta War Front, Colonel Olusegun Obasanjo recaptured the city of Oguta and did so on October 9, 1969. I was a Biafran child soldier that was transferred from the Oguta War Front to serve as a cook in the officers' headquarters at the bank of the River Niger at Ndone, Biafra. I served in the Biafran army for the 6 months that preceded the end of the Nigerian Civil War that ended on the 15th of January of 1970. My journey to the frontier of the supercomputer was a journey from the war front of Biafra to the science front of the United States. My technological journey to the frontier of the massively parallel processing supercomputer began on June 20, 1974, and began on a sequential processing supercomputer that was in Corvallis, Oregon, United States. However, that technological journey was bifurcated by racism, and discordant voices drowned the voice of the lone wolf research supercomputer scientist that was alone at the frontier of a new internet that is a new supercomputer. Who is Philip Emeagwali? The following story is a 60-minute excerpt from my 60-year story. At age 34 and at 10:15 a.m. New York time, Tuesday the 4th of July of 1989, the U.S. Independence Day, I saw something no human had ever seen before. I saw an ensemble of the slowest processors in the world outperform the fastest supercomputer in the world. I got goosebumps and my hairs stood straight while I watched that discovery. Seeing for the first time the slowest processors compute together to compute faster than the fastest supercomputer was the most amazing experience in my life. I was witnessing the birth of a new era in the history of the computer. I was witnessing a paradigm shift in the supercomputer world. I was witnessing a change of tectonic proportion that will be a change in the way we think about the computer. I was witnessing the birth of a new computer that is powered by an ensemble of 100 commodity processors, rather than computing with only one processor. I was witnessing the birth of a new supercomputer that is powered by a global network of 65,536 commodity off-the-shelf processors, rather than supercomputing with only one customized vector processor. I was witnessing the birth of a new Internet of Tomorrow that could be powered by a global network of 1 trillion processors that emulates one seamless, cohesive supercomputer. I was gazing across the centuries. For me, Philip Emeagwali, the massively parallel processing supercomputer was my supercomputing equivalence of a moonshot project. As a matter of fact, the fastest supercomputer cost as much as the spacecraft that took men to the moon. In supercomputing, the Holy Grail was to compute 1 billion times faster and to compute with as many commodity processors that compute together to solve extreme scale problems in computational physics. I began my quest for the fastest supercomputer on Thursday, June 20, 1974, at age 19, at 1800 Southwest Campus Way, Corvallis, Oregon, United States. 15 years later, I knew a thing or two about how and why parallel processing makes the computer faster and makes the supercomputer fastest. Today, my research interest has shifted to passing on my massively parallel processing supercomputer discoveries and inventions, and to passing them on to the next generation of quantum computer scientists. Back in 1974, no supercomputer scientist had any sense of how the massively parallel processing supercomputer could be used to solve the toughest problems in computational physics. And no supercomputer scientist understood what lies within the hood of a theorized massively parallel processing supercomputer of 1974. But today, the massively parallel processing supercomputer that was science fiction in 1974 is a reality that gave the petroleum industry the ability to extract more oil and gas from the Niger Delta oil fields of my country of birth, Nigeria. It should not come as a surprise that the petroleum industry purchases 1 in 10 massively parallel processing supercomputers. Please allow me to introduce myself. I invented a new internet that is a global network of 65,536 commodity off-the-shelf processors that are identical to each other and that are equal distances afar and apart from each other. And I invented how to use that new internet to make computers faster and make supercomputers fastest. Please allow me to take a retrospective look on my early supercomputing years, namely the 16 years onward of June 20, 1974, at Corvallis, Oregon, United States. In those 16 years, I conducted supercomputer research on how to harness the total supercomputing power of 16 massively parallel processing machines that were each powered by an ensemble of up to 2 to the power 16 commodity off-the-shelf processors that were married together as one cohesive supercomputer hopeful and married together by 16 times 2 to the power 16 commodity email wires. In the 1970s, I visualized each massively parallel processing supercomputer that I theorized not as a new computer per se, but as a new internet de facto. This series of lectures is on how and why parallel processing is the necessary technology for manufacturing the fastest supercomputers. In my lecture series, I will explain why my world's fastest computation that I recorded on the 4th of July of 1989 and that I recorded across the slowest processors made the news headlines in 1989 and was recorded in the June 20, 1990 issue of the Wall Street Journal. That experimental discovery of massively parallel processing is often remembered as my contribution to the development of the fastest computers and supercomputers. I experimentally discovered that a parallel processing supercomputer that is defined and outlined by an ensemble of the slowest processors can be harnessed to compute faster than the fastest sequential processing supercomputer and to compute faster than the fastest vector processing supercomputer. That experimental discovery is my contribution to the deeper understanding of the new internet that is a global network of processors and that is the fastest supercomputer of today. Ever since the supercomputer that computed automatically and computed with only one CPU was invented in 1946, the first real hope for computing across a billion processors did not emerge until I, Philip Emeagwali, experimentally discovered how and why we can communicate and compute across a new internet. That new internet is a global network of 65,536 commodity off-the-shelf processors, or a global network of as many identical computers. That supercomputer experimental discovery that I made on the 4th of July of 1989 made the news headlines in 1989. To make my invention of a new supercomputer, I used the most complicated mathematics from the world of physics, calculus, and computers. And I used that abstract mathematics to work out how to parallel process across a new internet that is a global network of 65,536 commodity processors. And I used that advanced mathematical knowledge to work out which data from my extreme scale computational physics codes to email and which data not to email. The new partial differential equations of modern mathematics that I invented and used was the cover story of the June 1990 issue of the Siam News. The Siam News is the flagship publication of the research mathematics community. The Siam News is published by the Society for Industrial and Applied Mathematics. The new mathematical knowledge in the Siam News is written by research mathematicians and written only for research mathematicians. On the 4th of July of 1989, I experimentally confirmed that I could use a new internet that's outlined by 64 binary thousand processors and use that new internet to solve the toughest problems in extreme scale computational physics and solve those problems by dividing each into 64 binary thousand problems and solve them 64 binary thousand times faster than one processor solving those sets of problems, those sets of 64 binary thousand problems alone. Since the first supercomputer of 1946, the technological need to solve the toughest problems in extreme scale computational physics is the primary source of inspiration for inventing the fastest supercomputers. In 1989, 9 in 10 supercomputer cycles were consumed by extreme scale computational physicists who constructed computation-intensive global circulation models or constructed highest resolution petroleum reservoir simulators or coded the toughest problems in computational fluid dynamics. My experimental discovery of the massively parallel processing supercomputer that occurred on the 4th of July of 1989, that occurred across a new internet that is a global network of 64 binary thousand processors, opened the door to the state-of-the-art new supercomputers that now compute 10 binary million times faster. That new supercomputer, in turn, creates a new computer science. Before my discovery, or in the 1980s or earlier, the 1,000 fastest supercomputers in the world computed with only one processor. After my discovery, or after the 4th of July of 1989, the 1,000 fastest supercomputers in the world parallel processed and computed with thousands or millions of commodity off-the-shelf processors. The economic importance of my experimental discovery of the modern supercomputer can be concluded from the fact that the fastest supercomputer cost the budget of a small nation. The story of how I got to do such an expensive supercomputer experiment and do it alone is the subject of another lecture. The massively parallel processing supercomputer is the most important tool at the frontiers of knowledge of computational mathematics, computational physics, and computational medicine. The sequential processing supercomputer and the vector processing supercomputer opened the fields of computational mathematics, computational physics, and computational medicine. And the massively parallel processing supercomputer continues to push the boundaries of human knowledge and push it across extreme scale science, technology, engineering, and mathematics. Parallel processing is at the root of the modern computer. Parallel processing changed and redefined the supercomputer from being powered by only one isolated processor to being powered by an ensemble of millions of processors. Within the massively parallel processing supercomputer is a world of magic in which we can foresee previously unforeseeable natural events and explain phenomena that our recent ancestors could not explain. In John 3:8, our biblical ancestors stated, and I quote, "The wind blows as it wills, and you hear the sound of its passage, but you cannot say where it comes from or where it goes. This is how it is for the children of the wind." End of quote. Due to the discovery of some laws of physics and the invention of the most abstract partial differential equations of modern calculus, and the discovery of how to solve the most large-scale system of equations of modern algebra, and the invention of a new internet that's a massively parallel processing machine that's faster than the fastest sequential processing supercomputer or faster than the fastest vector processing supercomputer. And due to that invention of parallel processing that enables us to do many things at once or in parallel, the 21st century children of the wind can say where the wind comes from. The modern supercomputer scientists and the meteorologists are the new children of the wind that were described in the Bible. But in the early 20th century, the meteorologists didn't have a supercomputer and therefore cannot say where the wind comes from. But by the late 20th century, the meteorologists did have a massively parallel processing supercomputer and used it to say where the wind comes from. Your television meteorologist told you where the wind comes from because her team of extreme scale computational physicists computed at the fastest speeds and computed using a massively parallel processing supercomputer and using it as the driving force behind the forecast of the meteorologist. It takes 3 decades to understand, discover, and invent the new physics, the new calculus, the new algebra, and the new computation, and the new communication that makes it impossible to say where the wind comes from. It took me 30 years to understand where the wind comes from. It will also take you 30 years to understand the answer that's blowing in the wind. I was once asked to give a 30-second answer to the question, how do we compute where the wind comes from? I answered, we compute the speed and the direction of the wind, and we compute them by employing the laws of physics to formulate an initial boundary value problem of modern calculus, and solving that initial boundary value problem that in turn is defined by a system of coupled nonlinear and time-dependent partial differential equations of modern calculus that encoded those laws of physics, and by employing a system of linear equations of algebra that approximated those systems of partial differential equations, and more importantly, by employing 10 binary million commodity off-the-shelf processors and using those commodity processors to solve those algebraic equations and solve them at the world's fastest speeds of computation. The massively parallel processing supercomputer is the essential tool that is used to know which way the wind blows and know the way before the wind blows. I experimentally discovered how to know which way the wind blows and do so across a new internet. That's de facto a new supercomputer. That new supercomputer wind forecast is called the evening's weather forecast. It was my fluid dynamical calculations of the 4th of July of 1989 that I executed across a new internet. That's a global network of 65,536 commodity processors that were identical to each other and that were equal distances afar and apart from each other, that brought me my first public recognition as a supercomputer scientist. I was asked to explain how I realized that on the 4th of July of 1989 that I had a breakthrough in massively parallel supercomputing, and to explain how my invention pertained to computational fluid dynamics. Back in the 1980s, 25,000 vector processing supercomputer scientists ridiculed, mocked, and rejected the massively parallel processing supercomputer. The June 14, 1976 issue of the Computer World magazine, that was the flagship publication of the computer industry, mocked the untried and the unproven parallel processing supercomputer of today, of technology. That June 14, 1976 article was titled, quote, "Research in Parallel Processing, questioned as waste of time." According to the guiding lights in the world of the computer, namely Gene Amdahl in the world of the sequential processing supercomputer, Seymour Cray in the world of vector processing supercomputer, and Steve Jobs in the world of the computer. And according to these three digital giants, it would forever be physically impossible to achieve a computer speed increase of a factor of 8 and do so in the world of parallel processing computer. at 10:15 a.m. New York time, Tuesday the 4th of July of 1989. I realized that I have massively parallel processed, and that I did so when I experimentally discovered that I have solved 65,536 initial boundary value problems of modern mathematics and computational physics. I realized that I have solved those initial boundary value problems, and that I have solved them simultaneously or at once or in parallel instead of solving them one by one or in sequence. My 16-year-long scientific quest for the experimental discovery of parallel processing was punctuated by several Eureka moments. My greatest Eureka moment was when I experimentally discovered that instantaneous supercomputer speed increase of a factor of 65,536 in the speed of my computational physics codes. I worked alone and I experienced those Eureka moments alone. I was the lone programmer of the first and the only massively parallel processing machine in the world that was powered by 65,536 processors. I was the lone wolf programmer at the farthest frontier of supercomputing. Because I worked alone, nobody else witnessed my moment of experimental discovery of the massively parallel processing supercomputer that I hoped will be the precursor to the modern supercomputer of today and hopefully the modern computer of tomorrow. Fast forward 3 decades, my moment of discovery is reproduced in every modern computer and in the fastest supercomputer, and was what prompted me. That experimental discovery of the massively parallel processing supercomputer prompted Steve Jobs to leave a telephone message for me. Not witnessing the first Eureka moment of the modern supercomputer that occurred at 10 a.m. the 4th of July of 1989 was like not witnessing the first human flight that occurred at the turn of the 20th century. Yet we accept it as an act of fate that the first human flight occurred, and we must accept it as an act of fate that the first modern supercomputer was discovered. I recognize that I had a breakthrough supercomputer discovery because the speed of my floating point arithmetical operations instantaneously increased, and did so by a factor of 64 binary thousand or 65,536. The reason my speed up of 65,536 days to 1 day made the news headlines was that it was a milestone in the history of computing. My proof that it was a breakthrough supercomputer discovery was that soon after it was clarified as a historic speedup, it became practical and cost-effective to manufacture supercomputers that computed in parallel. The first commercially available massively parallel processing supercomputers used 65,536 or more commodity off-the-shelf processors. Each processor was akin to a tiny computer. The modern supercomputer uses millions upon millions of commodity processors and uses them to compute in parallel and to reduce the time to solution of extreme scale problems in computational physics and computational mathematics. After my discovery, extreme scale computations that formerly took 180 years or 65,536 days of time to solution now takes just 1 day of time to solution. That extraordinary speed up was achieved when programmers massively parallel computed and did so across 64 binary thousand commodity processors. Back in 1974, supercomputer coding was like rubbing rocks until they caught fire. But after 15 years of daily supercomputer coding, the process of coding an ensemble of processors became easier. As a research computational mathematician, I translated my new calculus into my new algebra, and I translated my new algorithms for solving my new algebra into my new codes. And I translated my new codes from the blackboard to the motherboard. And I emailed my new codes across a global network of 64 binary thousand motherboards that in turn defined my new internet. Supercomputing across my new internet was like translating the Bible that was only written in the Latin language and translating that Bible into my ancestral Igbo language and then mailing 65,536 copies of that Igbo version of the Bible to as many Igbo-speaking persons in my ancestral hometown of Onitsha, Nigeria. Just as I had to have a command knowledge of the Latin and the Igbo languages in order to translate that Bible, I had to similarly have a command knowledge of physics and mathematics and computers in order to translate across those fields. My computational speed increased by a factor of 2 raised to power 16 because I used emails that I sent to and received from 16-bit long addresses. A perennial problem in parallel processing was to experimentally discover how to, for instance, map 64 binary thousand computer codes and map them to as many processors. Each computer code represents what computational mathematicians called an algebraic representation of an initial boundary value problem of modern calculus. For me, each computer code was akin to a general circulation model that I had to map to 64 binary thousand processors. I had to map those computer codes while maintaining nearest neighbor connectivity and maintaining a one-to-one correspondence between the codes and the processors. I was in the news in 1989 and in the June 20, 1990 issue of the Wall Street Journal because I solved that perennial problem of massively parallel processing across a new internet that I visualized as my global network of 64 binary thousand processors. I had assigned 65,536 initial boundary value problems to 65,536 processors. I assigned my computational physics problems to processors, and I assigned them with a one-to-one correspondence that maintained the much desired nearest neighbor connectivity that will be a precondition to my experimentally discovering the world's fastest speed in computation. I experimentally discovered how to assign initial boundary value problems to processors that each had its own operating system and memory. And I did so by using the binary reflected naming code that can be used in the X and or Y and or Z directions. My experimental discovery that occurred at 10:15 a.m. New York time, the 4th of July of 1989, was an emotional experience that words alone cannot describe. Sometimes it is difficult to translate thoughts from one medium to another. The article is written to be read on a page, but the algorithm is invented to be coded on a processor. And trying to explain my abstract supercomputer algorithms is like trying to rub rocks until they catch fire. On the 4th of July of 1989, I sat in front of my keyboard and computer monitor. I was shaking from my experimental observation. My jaws dropped because I was seeing supercomputer speeds and speedups that were previously unseen. I was speechless because I was staring at a new supercomputer. That first experience of massively parallel supercomputing was an out-of-the-body spiritual experience and an epiphany. Supercomputing 65,536 times faster and supercomputing across a new internet that was a global network of 65,536 processors was an experimental discovery that hit me like a thunderbolt. That discovery was the most cathartic moment in my life. That discovery was a visceral experience. That discovery was the birth cry of a new computer that is also a new internet. That discovery made me cry in my ancestral Igbo language. I cried, "Ewo, ewo, ewo." That discovery was cathartic because I realized that I possessed new and important knowledge that should move humanity forward. I discovered how to build a new supercomputer that is also a new internet. Daalụnụ, afam bụ Chukwura Philip Emeagwali, abụ m onye Ọnịcha. Bịa ga fụ m na emeagwali.com ka o mesịa. I'm Philip Emeagwali at emeagwali.com. Thank you. Thank you. Thank you. Thank you.
Insightful and brilliant lecture. Insightful and brilliant lecture.